So this is our second and our last lecture in Chapter 8 dealing with internal flow, so especially flow inside of a pipe. So you have a hot pipe, cold fluid, or switch it around, hot fluid, cold pipe, and you have a rate of heat transfer. We were able to predict the convection coefficient H. You know, the name of the game, or a lot of it, for convection heat transfer is finding the H. Okay, last time we did a lot of hydrodynamic considerations. Now we'll move more into the energy, Nusselt number correlations. We'll focus on laminar flow. How do you tell if the flow is laminar? You compute the Reynolds number based on the diameter. If it's less than 2300, you would call it laminar. And then we'll talk about turbulent flow. That would be when the Reynolds number is greater than 2300. And then once we've finished with circular tubes or pipes, then we'll take a look at non-circular passages like ducts, rectangular ducts or other things, and even concentric tube annulus. We skip and skip. We just don't have enough time to cover all of Chapter 8. All right, let's jump into it. So we talk about pipe flow, and we have the entrance to the pipe. Maybe I don't show it like that. Maybe I show it like this. And we run a coordinate system X from 0 all the way down. Okay. And we could have the wall of the pipe be subjected to a constant heat flux, and the heat flux would then be adding energy to the fluid as it flows down the tube. All right. So this would be Q double prime at the wall is equal to a constant. All right. We do have this notion of an entrance region, and then we have a fully developed. If the entrance region is a significant part of the overall length of the tube that you're analyzing, then you have a more challenging problem. The simpler is if you have a negligibly small entrance region, and then you just use the correlation as if it's fully developed. Even though there may be an entrance region, you neglect it. Last time we talked about predicting the temperature as a function of location X. And because the fluid is picking up an equal amount of energy from the wall, heat is being added for every uniform length going down, for every inch or meter or centimeter, whatever that length is, then the easiest one is to plot the mean temperature of the fluid. It's just going up and up because it's at the uniform rate, heat is being added. Q double prime is a constant. We then take a look at understanding H, the convection coefficient. Again, it's a little tricky because of the entrance region. You focus on the fully developed region, and you find that H is a constant in the fully developed region. In the entrance region, it's going to be larger. That's the big idea. It's not smaller. The H is larger. It's just like at the leading edge of a flat plate. The boundary layer is thinner, and you have a higher H. All right. The last one is a little harder, but it's plotting T surface. If you do it out here, the surface temperature is the same amount, like theta, the temperature difference is the same in the fully developed region. It's the same, because you look at the equation, you have Q double prime is equal to H times theta, or Ts minus Tm. And if this is a constant, and this is linear, and this is a constant, well, then this is linear a certain amount above it. 2 degrees higher, 5 degrees higher, something like that. And then you think about in this entrance region, well, what does the surface temperature do? Well, it can get very close to the mean temperature because the H is a lot higher. So be able to sketch the temperatures, the wall temperature, the fluid mean temperature, as well as the convection coefficient for pipe flow. Again, we're focusing on that fully developed region almost always in this class. All right. So what happens if you have constant surface temperature? You should be able to do the same. Pipe. Talk about a small entrance region. talk about the fully developed region as a function of location x going down. We want to plot the temperature. Here, because the surface temperature is what's constant, you might as well plot that one. That's easy. Ts is just a constant. And at some point, maybe start right here, you're going to pick up the fluid temperature, and it's going to have an exponential shape, Tm. Why? Because here you have a larger delta T that drive heat into it, but now it's heated up. The delta T that drive the heat is smaller, so it's not getting as much heat. It's exponential shape. If you went ahead and plotted the convection coefficient as a function of location, again, focus first on the fully developed region, it's constant. What about in the entrance region? Well, it's going to be higher. But again, we neglect that entrance region often in calculations or assume it's small. If not, you have to go with more complex equations for the calculation. Anyway, in here, it's like an exponential, but it's going to be not perfectly an exponential in that region. So that would be a plot of the convection coefficient, the mean fluid temperature, and the surface temperature. All right, let's do an energy balance. The energy balance, first we'll consider the constant surface heat flux, and then we'll also consider it for a constant surface temperature. We'll get a differential equation, then you can solve that differential equation. So in a section of the pipe, you have Q double prime is constant. So it's like what's coming in affects the change in the fluid. The change in the fluid out minus in. So you can go back to first law, you can think about your thermo 1 energy balance, and you would have some mass flow rate, you have the enthalpy, I'm going to call it like at x plus delta x, or you could call that state 2, state 1 at x. So the enthalpy going out minus enthalpy coming in equal to the rate at which heat is coming in. I'm just trying to relate this to your thermo 1 nomenclature, but we don't use that in heat transfer. What we have is we have Q times, this is Q double prime, times the perimeter times delta X, don't we? Isn't that the rate at which heat is coming into the control volume from the wall? What's P? Pressure? Perimeter. P is perimeter, pi d. Okay. And then over here, we still have the mass flow rate, but we're working with gases, liquids. We're really not changing phase. If you do change phase, you do have to work with enthalpy, but let's use a constant specific heat, and we're changing temperature, x plus delta x minus T at x. So you divide through by delta x. Do the limit as delta x goes to 0. What does that ratio right here do? That turns into the derivative. So you have the derivative of the mean temperature with respect to x equal to the Q double prime, the perimeter, divided by mass flow rate specific heat. Everything on the right-hand side is a constant. This is a nice differential equation. It's first order. We only need one additional condition. We would call the mean temperature, maybe at x equal to 0, is the temperature mean in. Temperature mean 1. So now I have a well-posed problem. Can you solve that one? You love this one. This is the easy one because it's a constant on that side. So you just separate, integrate, and you get that the mean temperature, the fluid mean temperature is a function of location. It starts coming in, Tm in, and then Q double prime times the perimeter divided by m dot C x. X is that length down the pipe. Straight line, just like we anticipated. Now let's warm up. Warm up for the harder case. The harder case is not constant heat flux, but constant wall temperature, isn't it? So let's take a look at the constant wall temperature. So same idea, have a pipe. Here, the temperature is a surface is a constant. We'll focus on a little region. That region you can think, if you're thinking of control volume, thermo 1, inlet state 1, outlet state 2, or here at location X plus delta X going down. And it's the same idea. It's what is the rate at which heat is being brought in from the wall into my control volume. That will be not a constant. Remember, it was Q double prime times the perimeter, right? Times delta X. What it is we still have our area, perimeter times delta X, but we don't have a constant Q double prime. So we have a convection coefficient, and we have the surface temperature minus the mean fluid temperature at that location. That's our rate equation at which it's coming in. Hopefully that makes sense. And then the same idea, we have the mass flow rate, specific heat, the temperature mean of the fluid at X plus delta X minus the mean fluid temperature at X. What do you think we do with this delta X? Bring it over here. What do you think we do with this? Do a limit. And then what we find is the derivative with respect to X is equal to, we have HP divided by M dot C times TS minus TM. Here we see TM, the fluid mean temperature is there as well as there. It's on both sides. The right-hand side is not a constant. It's a little more complex. But it's still what we call a first-order differential equation. What would be a good initial condition? Tm at x equal to 0 is equal to something like coming in. What does it come in at? Okay, now, can you solve this one? Well, the strategy to solve that one is probably to introduce a change of variable theta, where theta is Ts minus Tm at the location. All right. So this is by definition. Again, we're going to emphasize that theta is a function of x and Tm is a function of x. So when I differentiate this equation, d theta dx, the dt surface dx goes away because that's equal to a constant. We pick up a minus dtm dx. So our transformed with the new change of variables, instead of temperature, we have a temperature difference theta. This becomes d theta dx is equal to minus hp divided by m dot c theta. Where did that minus sign come from? Well, look at the definition of theta. And then we have the initial condition that theta at 0 is equal to theta initial, whatever it is, the initial temperature difference. Well, we solve this one, and so we'll get theta is equal to theta initial e to the minus hp divided by m dot cx. Yeah, it's our old friend the exponential. Again, what we did was we were working with a constant h. If you have an entrance region and you really want to do a good job of it, a lot of people have studied the entrance regions to tubes where you have a higher h. People have worked on that problem. Look in the textbook for more detail. It's as if we neglect the entrance region, we're in the fully developed region, it's a constant h. Okay, so we get a nice simple exponential. So there's the solution. So you could use this, you could use it to calculate what's theta at the exit given a certain length of pipe. Well, it'd be the temperature difference on the inlet, e to the minus hpl, where you put x is equal to L, the length of the pipe, divided by m dot C. Well, here's a little bit of a derivation. It's for a log mean temperature difference. Let me sort of summarize it for you here. So you have x equal to 0 and x equal to L. And you have an energy balance where you have that the flow times the temperature difference, that's the total heat coming in, the total amount over the entire area. Well, you just play by introducing theta and you get this equation. So the total rate of heat transfer into the fluid is equal to m dot c times theta inlet minus theta exit. I'm going to cast that like an equation where 1 is equal to that ratio. It's like I'm using this as a unit conversion factor. I come over here and I work from this equation where we left off, put it for x equal to L, that's what we had, rearrange, so you divide over by the theta, then you take the exponentiate both sides, or not exponentiate, logarithm of both sides, pay attention to the minus sign so it flips the what's in the natural log. Then I multiply by my 1. I don't know how else to do this. This seems to be dry mathematics, but it's pretty effective and pretty quick to get the solution that I want to, because I've gotten rid of the m dot c and I get an equation for Q, the total rate of heat transfer. So the total rate of heat transfer is equal to a convection coefficient, an area, and then some appropriate temperature difference that drives that heat transfer. And they call that the log mean temperature difference. Again, it's appropriate temperature difference that drives the heat transfer. It's from the pipe into the fluid. And this equation works regardless if let me see if I can draw it like this. Regardless if the surface temperature is like this, if the fluid temperature goes like that and then finally comes out of the tube, or if the fluid temperature does that or that, it works for the whole range of cases as long as it's an exponential description of the mean temperature as it flows through the fluid or through the pipe. So here's the definition. It's the temperature difference on the inlet minus temperature difference on the exit divided by the natural log of inlet over exit. Somebody says the natural log of A is equal to minus the natural log of 1 over A. That's true. And then you can re-express it like this. So instead of the inlet minus exit temperature difference, you could have exit minus inlet. And then you have the natural log of theta exit over theta inlet. Both of these are the same. Okay. You can play with this temperature, log mean temperature difference. If your fluid looks like this, let me introduce a new page, insert new page. Let's say the surface temperature is, I don't know, 100 degrees C, and the fluid inlet is 20 degrees C. And after a certain distance, the fluid temperature exit is 22 degrees C. The temperature of the surface is constant throughout the pipe. Well, what would you think the log mean temperature difference is? It's about 80 here and about 78 here, isn't it, the theta? The log mean temperature difference come in around 79. Check it out. Let's do it. Let's make the calculation. Delta T log mean is equal to theta on the inlet, 80, minus 78 divided by the natural log of 80 divided by 78. Somebody want to run that for me? Do you get that it's around 79?
79.0. Yeah.
79.0? Perfect. Okay. Let's do another. This is kind of the extreme where really the fluid's not changing temperature. But you could do another case. Let's do another case where temperature surface is 100, stays constant. The fluid comes in, temperature coming in of the fluid is equal to 20 degrees C. And let's say it goes out at 98 degrees C. Right? Well, in that case, what is theta on the inlet? 80, just like the first case. What is theta on the exit? 2 degrees. And that's a little more challenging. That's why we use the log mean temperature difference. In this case, you could have just said, oh, that average makes sense. But here's the log mean. What does that turn out to be? Delta T log mean is 80 minus 2 divided by the natural log of 80 over 2.
49.
21.1 degrees C. And the math work itself out. The log mean temperature difference accounts for that exponential profile in the temperature. Okay. Now we want to shift gears a little bit. We've talked about our temperature profile. What we want to do is we want to get a value for H, a convection coefficient. We spent a lot of time in this chapter so far building up to the main theme is I need to find H. Okay, well, what you do is you say, I have this pipe and I have the concept of fully developed laminar flow. What do you think the velocity profile looks like? This is U. It's a 2 times U mean, 1 minus R over cap R squared. Do you remember that? Yeah, that's our velocity, right? Velocity profile. It's parabolic. Okay, let's talk about temperature. Okay, let's say the temperature profile looks something like this, where here is the T at the surface, and this is the temperature everywhere in the domain as a function of the, usually we put these in terms of R, right? R going from 0 to cap R. Okay, can you solve for that temperature profile? Either for the case where you have a constant surface temperature, or you have the case for a constant wall flux. Well, we would say, give me a DE. What's the DE stand for? Differential equation. It's going to be an energy balance differential equation. It's going to look something like U partial of T with respect to X equal to alpha over R, the partial with respect to R of R partial T with respect to R. This is a term of diffusion of heat. The left-hand side is advection and how it would be increasing the fluid temperature as you're going down. We already know what U is. We just wrote it. There it is. You can substitute in there. We need some boundary conditions because it's second order in space. We'll take 2 boundary conditions. Let's say, can you pick out the boundary condition at R equal to 0? Something at R equal to 0. Can you kind of see that? What would that be? Would it be something like T at R equal to 0, or something about the derivative of T with respect to R at R equal to 0? Yeah, the derivative. And what about it? It's equal to 0. That's the easier boundary condition. Now, the second boundary condition depends on what's happening out here at cap R, right? What's happening at cap R? So maybe the easiest would be to think of the second boundary condition being a specified heat flux. Okay, so Q double prime at the surface, if that's equal to a constant, equal to minus a K, the derivative of T with respect to R at R equal to cap R. And I've got to think about the signs a little bit. If I turn this plot around and I put it like this is my center line. R is going out from 0 to cap R. As I've shown it, the temperature is low in the middle and higher out here at the edge, right? We're talking about a positive flux into the fluid, but that positive flux that's into the fluid is in the negative R direction. So I need to really do something like that to make the math work. Because isn't the slope out here positive at the wall? Yeah, it's positive at the wall. So anyway, here I have a nice boundary condition, 2 of them, a nice governing differential equation. You can solve this problem, right? When it's fully developed, the rate of change of the temperature as I'm moving down the pipe at any location R is the same as the rate of change of the mean temperature with respect to X. So I hate to say it, but this is where I'm just going to summarize some of the details, or all the details are in the book. But here are some juicy details. I used to love this section. And I would give lectures where the whole class was devoted to derivations. And then at the end of the semester, you know what the students left me for love comments on the surveys? They said, "Professor, how about some applications as well as some derivations?" So here are your derivations. All right. I'm just going to say it can be done. I set it up. I outlined it. If you're interested, what you can find is that you can get the temperature profile. But what did you want from the temperature profile? You wanted to be able to cast it in dimensionless terms and get a Nusselt number expression. You want to get H, the convection coefficient, and then you wanted to get the Nusselt number. Well, after a lot of work down here, what you find is when you have a constant heat flux, the Nusselt number, fully developed laminar flow, is a constant equal to 4.36. You're impressed. Well, guess what? That was the easy one. This is the harder one. And I just even say not separate and integrate. You have to do some other, like numerical approach to obtain the solution. And then you come out with the Nusselt number for a constant surface temperature application is a 3.66. There's some more digits on that. So in summary, if you're looking to find H, you get the Nusselt number because Nusselt is equal to H. The length scale is D over K, so H is equal to the Nusselt times K divided by D. That's how I find H. Okay, so you get dimensionless Nusselt number. If you find that you have laminar flow, how are you going to determine if it's laminar? Check the Reynolds number. Then you have to know if it's fully developed, neglect the distance to be the entrance region, to become fully developed hydrodynamically as well as thermally. You put thermal right there. Just if it's negligibly small, then you have a constant if for the boundary condition at a constant surface heat flux and another constant for constant surface wall temperature. Let's solve a problem. Water. U is equal to 0.02 meters per second. Is that the peak velocity, the mean velocity? If they don't specify it, it's a mean velocity. It's their average velocity going down the pipe. It's heated from the temperature on the inlet is 65 degrees C to the temperature on the exit is 85 degrees C. Is the wall temperature higher than 85? It has to be. Okay. The thin-walled tube has a diameter 0.0127 meters. Might as well convert that from millimeter to meter right away. It then has a tube length of 10 meters. Has a uniform heat flux. Aha! They've given me some key information there. And it's maintained by electrically a heater that's wrapped around the pipe. Neglect the entrance length of the tube. I was probably going to do that regardless, but I'm glad they said it. For fluid properties for water, use this value of rho, C, mu, K, and Prandtl number. So basically, you know if you're solving the homework problems that finding the fluid properties is not trivial. It's nice when it's given to you in the problem statement. To find the correct fluid properties, you have to pay attention to what temperature it's at, because these are now temperature dependent, especially the viscosity and the thermal conductivity. So pay attention to your temperatures. What is the heat flux required in order to make this goal? So here is what is Q double prime, which is a constant for this problem. And the answer is 519, right? So should I give you a minute? Let you work it out? Write down the equations that you're going to use in order to calculate it. So when we do a big control volume, right, we're going to go from 0 all the way down here to L. And then here's our big control volume. And we say what is coming into the water at the edge of the control volume is our wall of the pipe. That's going to be our magnitude of the flux times the perimeter times the length. Isn't that the total area that it comes in at? And then once it comes in, it makes the fluid hotter, it heats it up, so the m dot c times the temperature at L, or exiting, minus the mean fluid temperature coming in. And so you look at an energy balance, that's all that is, total energy balance, and you say, I'm looking for Q double prime, perimeter, length, mass flow rate, specific heat, exit, inlet temperatures are all known. So this is equal to m dot c divided by PL. What is perimeter? Pi times diameter, right, times the length. And then the exit minus the inlet mean temperature of the fluid. Those are given. So you do the math and it comes in at 5, whatever that is, 519 watts per meter squared. Now, what is my convection coefficient, part B? Well, do I know if it's laminar or turbulent flow yet? Have I made that determination? We need to check it to see if it's either laminar or turbulent. How am I going to check it? Run that Reynolds number. So the Reynolds number would be rho u d, that's our length scale, divided by mu. So when we run our Reynolds number, what do we get for that one? 600 and what? Yeah, it's not above 2300. The Reynolds number comes in 678. Is that what you got? Very good, thank you. So it's less than 2300, we conclude it's laminar. It's fully developed laminar flow with a constant wall heat flux. What is that Nusselt number? 4.36. Again, there's a number of assumptions in that. You know, that applies only to laminar flow, only to fully developed. And then it's the constant surface heat flux. Okay. So now we're going to recall the definition of the Nusselt to calculate the H, because the Nusselt is HD divided by K. So it's the Nusselt times the thermal conductivity divided by the diameter. And now we can calculate the convection coefficient. And doesn't that come in at 229? 4.36. Thermal conductivity 0.668. Diameter 0.0127. Anybody able to reproduce? 1, 2, thank you very much. 3, 4, thank you. All right, part C, what is the surface temperature of the tube at the tube exit? So the surface temperature, we're interested right there. We know the temperature of the fluid at the exit right there. It's going out at 85 degrees C. But what is the temperature of the wall of the surface at the exit? Well, we recall our rate equation, which works anywhere in the system, at the beginning, in the middle, also at the end. So we have that Q double prime at the end is equal to H times the temperature of the surface at the end minus the temperature of the fluid at the end. Maybe I should put it at E at the end. And we just calculated both the Q double prime and the H. So the temperature of the surface at the end is equal to the fluid temperature at the end plus Q double prime divided by H. It was 85 degrees C. That's a bad looking 85. 85 degrees C plus 519 divided by 229. Temperature surface at the exit comes in at a little over 85, 87.3 degrees C. You ready to press on? Yes, sir. I'm sorry? Oh, how do I find mass flow rate? Yeah, that's right. So the mass flow rate is rho, the fluid speed coming in, cross-sectional area. Yep. So this was rho um pi d squared over 4. And the mass flow rate comes in at 0.002468 kilograms per second. Look good? Yep, let's press on. If you do not have fully developed and you have to consider the magnitude or the length of the entrance region, the book doesn't let you down, but I'm not going to burn lecture time covering it. Go look at the figure in the textbook, and you can tell that the sort of the average Nusselt or the local Nusselt is higher because of some entrance region, but as it gets out fully developed, it just drops back to 3.66, or here for the constant flux. You can see it. So they worked out some of these cases. Let me press forward. Turbulent flow. What happens if you calculate the Reynolds number and it's above 2300? It's turbulent flow. Well, in your mind, you can think of this Moody chart, and you can think of the modified analogy, the modified Reynolds analogy. So I could figure out my Reynolds number, figure out my roughness, maybe come in here, pick up and read off a friction factor, stuff that friction factor into 1/8 times the Reynolds times the Prandtl to the 1/3, and I have a pretty good estimate of the Nusselt number. This is not the preferred method. Here are some other methods. Remember we did it for the Blasius where they curve fit down here for a smooth tube in a range of Reynolds number. Well, people have done that, and they've come up with correlations which are listed here. There's 3 of them. One is the Dittus-Boelter. This is probably the #1 fluid heat transfer correlation or equation out there, period. Everybody that takes a heat transfer class should know this equation. Maybe most of them know it by the name Dittus-Boelter, but they should know it some other way. As well as the Sider-Tate. It's neck and neck. Okay, if you go and study for the FE exam, you pull out the little booklet, you're studying for the heat transfer section, both of these equations are in it. Okay? So both of them are there. So we have a lot of turbulent flow in pipes, and we have a lot of heat transfer with those turbulent flow in pipes. So here it is, and you can tell for the Sider-Tate, you see this mu subscript S. That's a red flag, saying, oh, now I can see that they're going to make it simpler to evaluate the fluid properties, not evaluate the fluid properties at some appropriate film temperature, but evaluate them at some appropriate mean temperature of the fluid, and then account for the wall surface temperature through this property mu sub S. That's evaluating the fluid at the wall surface temperature. Now, there are other correlations. The book has a few of them. This is one worth pointing out because both of these are for smooth tubes. But if you don't have a smooth tube, well, it'll work for a smooth tube as well. But if you have where you're off of the smooth curve, you have a friction factor, you can stick it right in this equation. It's a little more complex, and you can use it for a rough tube as well as a smooth tube. All right? So these two are smooth tube only, smooth as well as rough. All right, so this is our Dittus-Boelter. McAdams has a textbook, well known. It was printed in 54. At least one of the editions was in 54. I have it on my shelf. The title of the textbook was Heat Transmission. And here is a quote out of the textbook talking about this equation. Maximum deviations were 43% to negative 33%. He's talking about the people who proposed that correlation and the experimental data behind it. It's plus 43 minus 33. It is clear that equations of the form of the products of the powers of 3 dimensionless groups, dimensionless group, dimensionless group, dimensionless group, each with a constant exponent, exponent 1, 4/5, constant. Or, what is that word? Inadequate. Look, these equations are going to get you in the ballpark, but you can still put 3 significant digits of your answer for us in this class. But believe me, out in the real world, there's no 3 significant digits on some of this. It's just the reality of the world. Okay? And there's a lot of people who have other correlations and propose, but they're not going to beat you up in this textbook with an equation that takes 2 lines to write it all out. So use a simple equation like this. It's used a lot. I don't think I've ever taught a class, heat transfer, where I didn't have the students use this equation, that equation right there, the Dittus-Boelter equation, on either one of the midterms or on the final. All right, let's move on. What happens if you have non-circular? Well, you go back and you say non-circular laminar, non-circular turbulent. And you work with the d sub h. Oh, I forgot what is d sub h? It's hydraulic diameter. It's a 4 cross-sectional area divided by the wetted perimeter. And if it's a round section, the hydraulic diameter is the diameter. But you use it especially for square and other different shapes. So this is the aspect ratio being changed. And what they do is they come in and say, this is boundary condition or this boundary condition. This is what people do in graduate school. They just like, oh, let's flush this all out. It'll take me a week or months to do it, but I'm going to figure it all out, right? And they work and they come up and they say, hey, it's 4.36 or 3.66. And for this case, it's this value, this value, this value. A lot of people did a lot of work. There you go. It's laminar flow. And oh, by the way, this is, remember in the laminar flow region, the friction factor is 64 over the Reynolds number for a round tube fully developed. So what they do is they plot friction factor multiplied by the Reynolds number. That's equal to the constant 64. Same thing is this is the friction factor times the Reynolds number for this geometry or that one. It's not 64, but there you go. These are all in your fluids book. Go look in your fluids book, you'll see that repeated. This is all new for heat transfer. What happens if you have you use the d sub h, you calculate the Reynolds number, and it's above 2300? I can't use those. It's not laminar. I have to use turbulent. So basically, use the hydraulic diameter and use the correlations based on a circular tube. Okay? Use the Dittus-Boelter with a hydraulic diameter. This is a section of the textbook I'm going to skip, but I point out that a lot of people have invested a lot of resource time figuring out how to enhance heat transfer and keep it compact. So they'll put wires, grooves, twisted tape, other things inside to promote the heat transfer in tubes, and they work. But there's nothing free. And so you're going to always have a penalty associated with pushing the fluid through there. It's going to have a greater pressure drop. You'll have greater heat transfer, but greater pressure drop. But these are out there in practice and used. Let's solve a problem. Air at a particular temperature enters a 2-meter long smooth rectangular duct with the cross-section, the rectangular duct's like this, where it has a 75, A is, let's say, 75 millimeters. This would be like A. And then B is 150 millimeters. We're going to spend the rest of the class time talking about this problem. All right. The duct is maintained at a constant surface temperature, Ts equal to 127 degrees C. And that's not the color I wanted it. And the air mass flow rate is so many kilograms per second. So we have this mass flow rate going down equal to 0.1 kilograms per second. Okay, I'm going to want to start making some calculations. So I busted this down, and the first part is I want you to struggle with, I need to get some fluid properties for air, and they're temperature dependent. And so what is going to be my temperature before I figure out, oh, the length here was what, 2 meters? 2 meters long, it's going to come out at a different temperature, isn't it? So it comes in at 12 degrees C. It's going to go out at some unknown temperature. And I'm going to have to check the Reynolds number. I'm going to have to know the viscosity. So right away, I need to get a temperature to evaluate the properties of air. What's a good temperature? So I'm going to pause. I'm going to walk around. And I want you to give me a temperature. Because that's what you're going to be faced with when you do homework problems. It's like, I got to have a temperature to evaluate the fluid properties.
Professor, it's so much easier if you just tell us.
Well, I hope my little discussion here helps you when you do homework. But you're going to have to do this. It's like, I need to know this exit temperature because then I could calculate some appropriate film temperature. Let's say the film temperature would be the average of the average mean temperature of the fluid would be 12 plus some exit temperature, right? Divide by 2. I'd add that to the surface temperature of 127 and divide by 2. Is that what you ran like that? Something like this? So what did you exit? What's your exit temperature? I don't know, 50. Guess 50, right? So then you put in 50 plus 12 divided by 2, add to 127 divided by 2. I don't know what that comes out at. But then we need it in Kelvin, so then you add 273 and get it in Kelvin. So a lot of you are coming in, oh, I think around 340, 345, and nobody really went for 350, but that's what I went for. I said 350, boom. And then I went into the table and I got rho, specific heat, mu, K, and Prandtl number, right? You know, and you just collect these properties. After you solve a few of these problems, you know these are the properties you need. You could calculate or collect nu, and you could collect alpha as well. All right. But now we're ready. We struggled a little bit with that, starting this problem with properties. But now the question is go through it blow by blow. Same problem. Here are all the properties at 350, 1 atm. The density, specific heat, mu, K, Prandtl. Calculate the hydraulic diameter for the duct. There's our duct like that. It's 75 by 150 millimeter. So I want to see how many people can calculate this hydraulic diameter. I'm going to pause, walk around. Can you do it? So the A and the B, so the perimeter is 2 times A plus B, and the hydraulic diameter is 4 cross-sectional area divided by perimeter. The cross-sectional area is A times B. And you put in those numbers, and this comes in at 0.1. Good. Now let's move to what's the Reynolds number? Reynolds number, using that hydraulic diameter for our length scale, it'll be rho, the mean speed, hydraulic diameter divided by mu. We're given the rho, we're given the mu. Do we have our speed? It's got a mass flow rate given, so we're going to have to calculate that. The mass flow rate is rho u cross-sectional area. So U is equal to m dot divided by rho cross-sectional area. All right, the speed 8.933 meters per second. Anybody get that? Yeah. And then the Reynolds number comes in at 42,735. Laminar or turbulent? Turbulent. Don't use 4.36 or 3.66. Nope, nope, nope. Remember, what is our Nusselt number? You could use Dittus-Boelter. You could use Sider-Tate. You could use another one with the friction factor if you wanted. What's the easiest? The one, if you use them a couple times, you'll see the Dittus-Boelter is easy. So it's 0.023 Reynolds to the 0.8. Prandtl, because it's being heated, it's to the 0.4. If it was being cooled, it'd be Prandtl to the 0.3. A lot of times I'll just forget the 0.4, 0.3, and I'll put it Prandtl to the 1/3, 0.333. Look at the Prandtl number for air. It's 0.7 anyway. It's not going to make a big difference. But keep it consistent with the textbook, Prandtl to the 0.4 power. Okay, so you run this one, and we calculate the Nusselt number is 101. That's using the Dittus-Boelter. Now, what is the convection heat transfer coefficient? H is equal to, how am I going to calculate that? What's the definition of the Nusselt number? HD over K. So it's the Nusselt times K divided by the hydraulic diameter, the diameter that we're using. And that comes in at 30. Make sense? All right, once I do that, how do I get that the outlet air temperature is 39.2? I'm going to pause. How do you calculate that? How do I get the outlet? Well, do you remember our discussion about the temperature as a function of location? And in this problem, our surface temperature is 127 constant. And we come in a really low temperature of 12 degrees C, and it's going to maybe crawl a little bit or really get up there and go out at nearly that exit temperature of the wall. Surface temperature, right? We don't know. But we already worked the math, didn't we? Didn't we already get an equation for this? Let me get rid of this one. Let me draw it like this. Isn't that theta? Didn't we come in with an equation that theta at any location X, we're going to be interested in evaluating at L, so you might as well say theta at the exit is equal to theta at the inlet times what? E to the what? H, P, L, that's using X instead of L, or L instead of X there, divided by M dot C, and I forgot the minus sign. Does that equation look familiar? Yeah, that equation looks familiar, doesn't it? And so what we can do is we can put in our theta initial, 127 minus 12. We could put our exponential. We worked so hard to get that Nusselt number of 30 and the convection coefficient of 30.3. Our perimeter, I'm not going to substitute. You already did it over there. Your length is 2 meters. That's our length right up here. And we had our mass flow rate, where is it at? 0.1 kilogram per second. And our specific heat, 1009. Pay attention to the units. Sometimes the specific heat's in kilojoules per kilogram degree C, so watch out your units always. And we find that the theta exit comes in at 87.8 degrees C. And then you can back out that the temperature exit is the surface temperature minus theta at the exit. And so the exit temperature comes in at 39.2. At this point, you could update your estimate of the good film temperature for this whole problem. And you'll see, I think, that it's close to 349 Kelvin, close enough to 500 Kelvin. Do not do another iteration. Even if you were at 340 Kelvin, your first guess of the fluid temperature, I would say that's close enough. But at least once in your life, iterate. Long, just do it. It's like, painful, but you do it, okay? All right, we changed the problem. We have 4 minutes left, and we make it a galvanized steel surface with a roughness of 0.155. It's not a smooth duct anymore. What do? Does it change the hydraulic diameter? No. Does it change the Reynolds number? No. Does it change the Nusselt number? Well, yes, because we have to use a different correlation for that Nusselt number. It was 101 for the Dittus-Boelter, wasn't it? But if you go and you try the GNIELINSKI, that other correlation, which uses the friction factor, you'll get a different estimate of the Nusselt number. That will come in at 98.2 versus 100. Or you could just use the modified Reynolds analogy. What was that one? That's the friction factor over 8 Reynolds Prandtl to the 1/3 is the Nusselt number. If you use that simple equation, you'll get that the Nusselt number is 109. 101, 98, 109, you're in the ballpark. But because I think it's this roughness right here, I picked that one. I think the Nusselt number would go up because then the H, the convection coefficient, would go up. Wasn't it before lower? Wasn't the convection coefficient around 30.3? A little roughness, it's turbulent. Okay, 32.7. Not a big change, is it? And then your exit temperature you can update because you have a better estimate of H, and you get it 41.1. Instead of before, what was it? 39.2 degrees C. Essentially the same, but you had a little roughness in there. Well, with that, I remind you that we skipped these last sections of the textbook, and hopefully you're well on your way to solving these problems. I'll be in my office if you have any questions. Thank you for your attention.